I started talking to you about Newton's laws, but I got cut a little bit short, and I want to say a little bit more about that. So let's think about, I want to just talk a little bit more about inertial frames of reference. And I guess this would be in the Galilean sense. I don't know how to spell Galilean. Oh, well. I'll look at both of them. I feel like I need it. Anyway, it's okay.
It's physics, not English.
He's been that wild, you won't notice. I don't know that he's. Okay, anyway, inertial frame of reference. So suppose we have a frame S and another frame, let's say S prime. Okay, so in particular, you can talk about the position relative to, relative to S prime would be equal to the position of the origin. All right, that's the position of the origin of the S prime system, of the S system rather, plus the position with respect to S. All right, so let's see here. Roughly speaking, this is the picture. So let's see here. Which would be which in my picture? Here's S prime. Here's S. Right. So I'm thinking about some particular body, some material body. It's moving through space, whatever. And at some particular time t, you can either measure its position with respect to the S or the S prime frame, right? So you either got this here, what we would call R sub S prime, or you could write this guy, which I would just call R sub S, right? And so as you can see, I have messed up the equation. What should I write? R sub S is equal to R sub dot plus R sub S prime, right? There we go. That makes sense. Then what? You differentiate this, and you get the velocity measured with respect to S is equal to the velocity of the coordinate system moving plus the velocity measured with respect to the moving coordinate system, right? And then finally, if you differentiate again, you get the acceleration measured in the S system is equal to the acceleration of the coordinate of the origin plus the acceleration as measured in the other coordinate system S prime. So here's definition. Definition. S and S prime are inertially related. Inertially related if this A sub 0 is equal to 0. In other words, if the origin of the moving frame is not accelerating, all right, in the other frame, in the given frame. So the given frame S is thought of as being a fixed inertial frame. Okay. I suppose if you wanted to be weird, you could think of S as being a moving coordinate system and then S prime being a similarly moving coordinate system, but I don't see that done as much. It kind of hurts my head to think about it a little bit. Okay, so then what? So what does that mean? Like, if that's the case, if A sub 0 is 0, then how are S and S prime related? That's what? That's dV naught, right? dt, that being 0, what's that say? V naught is equal to what? constant vector, let's say v, right? Well, I guess I should use some other letter. I don't know. You guys pick a letter, any letter. L? Okay. Constant vector L. I'll take it. But then that's equal to what? dr not dt, right? Notice that my use of sub naught here is not the initial time like we usually have been doing. Here, sub naught is referring to the origin, so dr of the origin. So if it's bothering you that I'm using sub naught in a different way, you can take all of these sub naughts and rewrite origin. It's just going to get tired about the 10th time I write origin. But understand that that's for origin. Okay, then what I can do? Integrate again, right? So this says r naught of t is equal to t times L plus yet another vector. Let's call it m, since we're writing on L. So what is this? Can you tell me what this means? How are S and S prime related then? This tells me how S and S prime, how the given inertial frame and the inertially related S prime frame are related. How are they related? Linearly. Linearly? Okay, but can you tell me in terms of old-fashioned language? S and S prime are what? I mean, linear? And I keep hearing linear, okay. How about S prime is moving at constant what? Velocity with respect to the S frame, right? Now, maybe you were taught these words sometime earlier in your life. A lot of times people used to say that S prime is under uniform rectilinear motion. Which is just a fancy way of saying it's moving in a straight line, all right, at constant speed. Which kind of gives you a couple choices. One is that the speed could be 0, right? In that case, the coordinate systems are related, like in a very simple way. They're just a shift. Like, for example, you can talk about the origin coordinate system based on like the corner of the room over there, right? Versus the origin, you can put it up in the upper corner over there. And so to relate those two different coordinate systems, you just add a fixed vector to get from one to the other, right? You can have more complicated systems where two different coordinate systems are related by adding some vector which is changing with time, right? Like you could compare the Earth frame, for example, to the like frame of reference for a train. That would be another example, slightly more interesting. Again, assuming we're when I say that I'm in what? I'm neglecting the rotation of the Earth and all that fun stuff. Okay, so what's the point of all this? You guys know what are Newton's laws? What's the first law? An object remains in motion unless acted upon by and what kind of motion? Object remains in uniform rectilinear motion, right? Unless acted upon by an outside force. So what's Newton's second law? What's that say? It says that the net force that acts on a body is equal to the inertial mass times the acceleration of the body, right? So Newton's second law, think about that for a second. Basically, the net force is equal to the mass times the acceleration, right? So, if the net force on the body is 0, what's that say? Acceleration is 0, okay, suppose this. Yeah, then that implies that the acceleration is equal to 0, which, by the way, implies that the position is equal to some initial position plus times some initial velocity. sorry, I'm using R naught and V naught in a different sense. Let me give them a different name. R Pac-Man, V Pac-Man there, fixed it. But you'd be like, wait a minute. So Newton's first law says that if an object remains in motion on a uniform rectilinear motion unless acted upon by an outside force, right? But Newton's second law says that if the force is zero, calculus, right? Calculus happens, and you get that the position is uniform rectilinear motion. So why do we need Newton's first law? I mean, isn't Newton's first law just a consequence of the second one? In calculus. I don't know. People have written books about this stuff. You can come up to your own conclusions. But anyway, these laws are not independent, right? Now, what my PhD advisor would say would be that Newton's first law is really just a statement of existence. What Newton's first law really says is just that there exists an inertial frame. There is some coordinate system on the basis of which you can do physics. Once you have that one inertial frame, then you can look at a whole family which are inertially related to a given inertial frame. And in any of those other inertially related frames, you can do physics. How do you do physics? Well, Newton's second law tells you the net force is equal to m times a, and that's that. Let me look at an example with you guys. Now that I got that out of my system. You're like, well, that's good. I don't want to see any more of that. Now, for the most part, we just stick with one frame of reference, right? And I don't do things with respect to two different frames of reference, but because, you know, we have enough trouble with one frame of reference, much less two, right? So what I'm doing at the moment is a little bit out of order, but I hope you can forgive me for it. I need to get it out of my system. And then we will do stuff like your web design for the most part. So here's a fun example. This is from lecture 8. All right, so here's one. Suppose you are in an elevator, all right, and the elevator accelerates upwards at 1 meter per second squared, all right? So that's the elevator frame of reference is an accelerated frame, all right? So with respect to the Earth's frame of reference, right, where this elevator is built, this would not be an inertially related frame, right? You could not assume that the accelerations are the same in the elevator and on the Earth frame. There's going to be an adjustment because the frame is accelerated. So the question is, what's the normal force on your feet? All right, so we haven't talked about normal force yet, but here's the deal. So you think about Mr. Top Hat in this elevator, right? And there's basically two forces acting on him. There's the force of the elevator floor pushing up on his feet, upward, right? And then there's the force of gravity, which is very boring, always same direction, down, you know? Sorry. I mean, some people try to advertise different and they pay admission to go to these places, but the truth is they just build buildings sideways. It's not really, gravity's still pointing down, it's just the building is sideways, if you know what I'm talking about. There's some place. No, you know, there's some iron deposit in the hill or something that makes the gravity stronger. Nonsense. They're just building the building sideways. So, you know, save your money. Okay. My apologies to the owner-operator, Mystery Hill. Yeah.
Have you been to that house?
Yeah, sometime ago. But there's really not that much to do around mountains, North Carolina, so I mean, you'll go to this place eventually out of boredom. But okay, so Newton's second law says that the mass times the acceleration. Okay, the mass times the acceleration is equal to the normal force plus the force of gravity. Why? Because those are all the forces that are at play. That's it for the system. As I think about Mr. Top Hat, the mass here is the mass of Mr. Top Hat. I'm given that the acceleration is 1 meter per second squared. All right, so put that in. I know that the force of gravity is mg. Now, this is also called the weight, right? M times g is the weight of Mr. Top Hat on Earth, right? Very specific force. M times g is weight. That should be distinguished from the mass of Mr. Top Hat, which is m, right? Weight is a force. S is mass. Okay, so solving for n, you see what I get? I get that the normal force is the weight, which would be mg, plus this m times 1 meter per second squared. In other words, his effective weight is actually it's larger, right? You felt this too, right? If you compare the normal force as you experience it on the bottom of your feet just standing here versus when you're in an elevator. In any other building, you could feel the elevator going up, right? Because it's like kind of like speedy. There's that sense of acceleration, that sense of urgency as you're going to the next floor. You know what I'm talking about. You've been in other elevators in other places. I mean, I can't talk about the elevators in this building, but other buildings. You'll experience the acceleration, right?
Sears Tower, that's a nice elevator.
Sears Tower, for an extreme example, yes, very good.
It goes fast.
Now, so just a word or two here. So your effective weight is larger than your standard weight when you're in this elevator because it's an accelerated frame of reference, right? An accelerated frame of reference brings into bear what are called fictitious forces, so-called frame effects. So in particular, if you were to assume that the elevator was not an accelerated frame of reference, right? Suppose it's all dark out and like you don't know that you're in an elevator. You're just going up. What would it feel like? It would just feel like you would just think that the gravity was stronger, right? Like you would know that you're accelerating upward, right? You would just experience a stronger gravity. You couldn't tell the difference, right? If you think about it, like imagine just darkening the windows and you wake up in this thing that's always accelerating upward, you know? You would just think you ate too much yesterday or something, I don't know. I mean, you feel heavier. So this is the interesting thing though. So if you assume then, if you look at and what is that frame of reference? That would be the frame of reference based on putting the origin on the elevator itself, right? With respect to the elevator itself, Mr. Top Hat's position is just constant. It's just, he's just there, he's standing there, right? So the acceleration with respect to the elevator frame of reference is zero. So if you believe in Newton's second law, from the perspective of the elevator, you say the sum of the forces is zero. Right? Now from the perspective of the earth frame, you realize that that's a lie, right? Because, I mean, that's the debate. So from the earth frame of reference, you can recognize that this term over here, which you would think of as a force from the perspective of the elevator, isn't really a force, it's a fictitious force, because it's really nothing more than the effect of coming from the accelerator, I keep saying accelerator, but the elevator accelerating. So this was Einstein's giant leap. He was like, well, what makes these fictitious forces frame effects is the fact that they've got some proportionality to mass, right? So Einstein was like, so maybe gravity is also fictitious then because it's got this dependence on mass. The formula for the force itself has a dependence on mass. And he was able to chase this idea down. About 1916, he came up with general relativity, which is essentially based on this observation at its most kind of basic level. This idea that gravitational force itself is a fictitious force. It's just a consequence of us being in an accelerated frame of reference. Gravity is a frame effect. But anyway, that's not part of this course. Why did I just say it? I don't know. Now, just to give you context, what are other forces? What do I mean gravity is different than other forces? Here are other forces. There's like, for example, the force of the spring force has a formula minus kx. Is there any mass dependence? No. The spring force just depends on the spring constant at x. All right? Another example, that's my one example.
Friction.
Oh, friction, thank you. No, that's gravity. Got a mass dependence also. I'm sure there are other examples. That's mostly the one we'll do. Pretty much everything else is gravity, one way or another. Yeah.
Light pressure.
Light pressure. Okay, well, I'll take it. Another example. And then I'll put this slide away. A squirrel with initial speed v naught goes distance x naught into a tree. All right. So here's the squirrel. Use your imagination. And then it goes a distance x onto a tree. I mean, if you like squirrels, you can assume that it's resting, whatever. And I'm just assuming that the squirrel decelerates uniformly. Okay, so then what would the necessary braking force be applied to the squirrel from the tree? Assume that the mass of the squirrel is m naught. All right, so we can figure out acceleration because we know how to do it, constant acceleration, right? Timeless equation, right? You got this distance, you know, you're starting with velocity v naught, you're ending with velocity 0. So you just solve 0 squared equals, 0 squared equals v naught squared plus 2a delta x. And that will give me the relation between the braking distance and the initial velocity. And that, in turn, will then tell me the acceleration. The acceleration is minus v naught squared over 2x naught. So what's the force then? Well, force is equal to m naught times a. So the corresponding force would be minus m naught v squared over 2x naught. And of course, you could put some specific numbers in there to capture the proper velocity of the squirrel and how much distance it would take to stop it. I don't know. If you would like some better ideas about how to estimate that, you could maybe ponder this picture. Something like this. You've got, maybe 1,290 meters per second. That'd be a typical flying squirrel speed. Mass of 1/1000th of a kilogram. Okay, kind of odd. Seems more like a bullet. And then that's what it would look like, something like that. So they can give you some ideas. About 5 to 10 meters. Something like that. I will put this away now. All right, first let me do an easy mathematical example for you guys, and then I'll get into start our work on the inclined plane problem, perhaps. Maybe not today. Maybe I'll do inclined plane next time. I think today I'll just do box on a plane. We can do inclined plane next time. Okay, so first the mathematical example. So here's the example. Suppose you have a mass equal to 10 kilograms, and your position as a function of time is measured to be, x naught e to the alpha t times x hat plus parentheses y naught minus 1/2 gt squared y hat. Maybe I should just say that who cares about numbers? Let's just say m is equal to m naught. There we go. So I want you to find the force responsible for the motion. You notice that all of this is done with respect to, thankfully, one frame of reference. Okay. So what do? We know what Newton's second law says, F is equal to ma. I've got the position. I want to find the acceleration. What do? Yeah, differentiate twice. So the acceleration is equal to d squared r dt squared, which is ddt. Okay, so what's the derivative of this? It's alpha, x naught, e to the alpha t, x hat, plus parentheses, derivative of y naught is 0, right? So I get myself a minus gt y hat. New marker. And that's equal to, my excitement was premature. That is equal to, so differentiate this again, what you get, alpha squared, x naught, e to the alpha t, x hat, just rides along, right? And what's the derivative of gt? Minus gt is just minus g y hat, right? So there you go. That's the acceleration. So therefore, the net force responsible is equal to m naught times parentheses alpha squared x naught e to the alpha t x hat minus g y hat. There you go. terms of interpretation of what this example means, what on earth would be this sort of force, the x hat term? I have no earthly idea. I just made it up because the math wouldn't be that hard. But I can tell you what the second thing would be. What would that be?
Force of gravity.
Right. This piece would correspond to minus m naught gy hat, right? Which you might think of as the force of gravity near the surface of Earth. Near Earth's surface, right? But anyway, if I give you a position as a function of time and ask you to find the force, this is actually not a hard question. It's really just another, hey, can you differentiate distinct points question? Which is a meaningful question because there's a sizable portion of you who are still struggling with that. And it's important that you learn that kind of basic calculus stuff before you leave your... All right. Well,
Are we going to need to know like trigonometries or anything for calculus solving problems here?
I could work that into testing.
No,
You need to know trigonometries. Well, to solve the last problem would have been helpful. For example. But yeah, we need to know trigonometries. Always. Okay, so here's a better example. So find the acceleration. Acceleration. A box. And let's say the mass of the box is 100 kilograms. And let's say it's pushed with force F naught equal to, say, 500 newtons at theta equals to, I don't know, 30 degrees above horizontal. Right, and I need to tell you a little more. And this is on a frictionless surface to start with, okay? Flat surface. We will, before you know it, make the surface have friction and put it on an angle. But this is a good starting point.
Did you already put it on an angle?
The force is at an angle, but not a box.
Oh, okay.
But let me just draw a picture and then it'll become clear. So what I'm talking about here is something like this. Here's the box. Here's the horizontal. Just I'm saying the force is put like this. So the box is. So the question is, what's the acceleration of the box, right? All right. So let me just draw a bigger picture. All right, and I'm gonna. It doesn't really matter where you envision the force pushing. I'm gonna envision the force pushing up here instead. Okay. All right. So here's my 30 degrees. So the key for all these kinds of problems is a free body diagram. Right, what's a free body diagram? It's just a convenient picture which illustrates the net force on a particular material body. Basically, you isolate all the different forces that are at play, and this free body diagram illustrates them. Right? So if you think about this force, think about this body, what are the forces at play here? Here, I'll tell you. On the one hand, you got the normal force, which acts upward. Now, you'd say the label N for normal force is somewhat questionable. We'd use N for newtons. You got me there. Maybe I should use F for N. I will invariably use N though, but find the normal force. That points up. The normal force, now pay attention to this, is normal to the surface. So what direction does the normal force go? Right, perpendicular to the surface. This is always the case, okay? So that's why it's the normal force. I know it doesn't sound like I'm saying anything, but trust me, I'm saying something. Now, there's also gravity, which goes like so. And actually, this would be the weight. Now, the weight of the box would be mg, downward, like so. Right? In the free body diagram, you draw all the forces as if they're acting at one single point, right? So the other thing I have, of course, is the pushing force, which I called F sub naught. So the sum of these forces is the mass times the acceleration, right? So the net force is mass times acceleration. Now, that's a two-dimensional vector equation, right? But only one of those directions is really that interesting. I mean, they're both interesting, I guess, but what's the acceleration in the y direction?
0.
It's 0. I gave you that when I told you it was sliding along the plane, right? So if I tell you the box is on the plane, I am basically telling you there's no y acceleration. So that's easy enough. So the net y forces is equal to 0, and net x forces is equal to the mass times the acceleration. Right? That's the big picture. Okay, so then what are the net x and net y forces? So what are you guys doing? Some manner of dark magic, yes? So you guys are telling me I can decompose F naught into its vector resolution into its Cartesian components, yes, no? As I have illustrated in red there, you can break that diagonal, that slanted vector into these two perpendicular horizontal and vertical vectors, which we can build F naught from, right? So in particular, I've got F naught cosine 30 x hat, and I've got minus F naught sine 30 y hat.